Hey, so in this video I'm just going to introduce mesh analysis, talk about how we can use it to solve for unknowns in circuit problems, and then solve this example here that we see on the screen to figure out what the currents are going through each of the resistors, and we're going to use mesh analysis. And then in the next couple of videos we'll do some more complicated examples so you can get some different ideas of how to apply this. So when we're doing mesh analysis, you have to identify each mesh, and each mesh is basically each loop that's going around in the circuit without like incorporating other loops inside. For example, if you start here, we have one loop that looks like this, right, just back to this point, and we have another loop over here that we can go around the circuit and basically get back to the same point that we started. So we're going to eventually apply Kirchhoffs voltage law around each of those loops, but what you do is you actually identify, like you just kind of draw on what we call a mesh current that's flowing around each of these loops. So we'll say we have I1 going around this loop, and we have I2 going around this loop. So these mesh currents like sort of do exist and sort of don't. In cases where they're like flowing through just a single resistor that's not like between two meshes, then it will sort of be the actual current that's flowing through. We might have the sign backwards, but the magnitude will be the same. And then for elements like this, where basically the actual current that's flowing through an element like this is going to be the net of both of these. For example, if we want to draw the 1 ohm resistor just like this, it's going to have some current. Let's just say whatever the current is, maybe let's just assume actually some currents for all of these. Let's say that we just assume that IA is going to go this way. We're going to assume that there's another current here. We're going to call it IB, and we're going to call it there's just some other current here that's going down through this resistor. Let's just call that IC. We can just kind of assume the directions. It doesn't actually matter. And if we find to get negative magnitudes here for these, then we're going to determine that we've just got them in the wrong direction. But looking at IC here, then, when we're coming down into this resistor, we have this mesh 1, which is going this way, I1, and we have this other one, which is going up, I2. And so really, IC is just going to be equal to the sum of the vectors that are going this way minus the vectors that are going that way. So it's going to be, sorry, that was I1. So we have I1 minus I2. But if we look at this, I2 is going counterclockwise around the loop this way. So I2 is coming down like this. So we have I2 is going this way, but we know that 1.5 amps is going up. So we know by inspection that actually that I2 is going to be equal to negative 1.5 amps. So we can write that, for example, we can just say I2 is equal to negative 1.5 amps. And then here, if we look at this resistor, we were saying that I2 is going this way, right? It's like passing through this resistor like that. But if I2 is going this way and it's a negative 1.5 amps, that means we can just switch the direction, and this is going to be the actual current that's flowing through the resistor is going to be 1.5 amps flowing to the left. Now the way that we drew IB is actually turns out to be in the correct direction, which is matching the direction of, the actual current in the branch. So we can even just write it here that IB is equal to 1.5 amps. That is going in the direction that IB is labeled on, and that's also going to be equal to negative I2. And then when we look at the other loop here, we've labeled on, we've assumed a direction for the current that's actually flowing through this resistor to be going to the right, but that matches what we have for I1 because I1 is spinning past, it's going that way. And so I1 is going to be equal to IA based on the way that we've assumed these. So we have IA is equal to I1. Now, when you're doing mesh analysis, it is most common to write your mesh currents, which are I1 and I2, going clockwise. And if you basically always draw them clockwise, it just like reduces your chance for screwing up later, especially when you come into situations like this, because you kind of just, you always have the same form here. So that's always the first step in mesh analysis, is to draw on the mesh currents and write down any information that you have. For example, in this case, we were able to solve what this one is really easily, and then even based on that, we were able to find out what one of the actual branch currents is in one of these elements. Generally, to find the rest of the information, we're going to need to apply KVL, Kirchhoffs voltage law, in each loop. For example, this one we've already solved, so we don't really need to do anything here. So for the rest of this problem, we would only need to apply KVL in this loop. So let's do that. Let's write KVL, loop 1. And If you remember from KVL, we basically just take the voltage drop or voltage gain across every element, and we pick a starting point. So like, let's just start here. And when you enter through the negative terminal, depending on which sign convention you follow, I like to follow the passive sign convention where you enter in a negative terminal and you assign that a negative value. And when you enter the positive terminal of an element, you assign that with a positive value in KVL. So that would be a plus and a minus. And this would be a plus and a minus and a plus and a minus. And that's based because current is always flowing into the positive side of a resistor. And we've assumed that that's the way that these currents are flowing. So if you want to go with that, let's just remember that Ohm's law is V equals IR, and KVL, we're just like summing up all of the voltage drops and gains and setting it equal to 0. So when we start at this red dot here on the bottom, we're going to come into the battery and we're going to assign this a -3 for the voltage. So we have -3. And then when we enter in the positive terminal of the resistor here, we need the voltage drop, but the voltage is equal to the resistance times the current. Now, I find it helpful to actually start off with the currents that you've kind of labeled on, the assumed currents through each branch, but you'll see why. You can skip to the next step if you want, but I find it more straightforward and like less chance of making errors if you do it this way. So the voltage drop across this element is going to be IA times the resistance. So we add that because we come in the positive terminal, and we have 2 times IA. The units of this term are going to be in volts, and I'm just going to drop all of the units here just to keep it like less stuff going on. And then the voltage drop across this, we're going to have a positive because we're coming in through the positive terminal, and it's going to be the current times the resistance. So IC times 1 ohm. And we set all of that equal to 0 because basically when we come back out here, we're back at the point that we started at. Okay, so at this point I would substitute IA and IC for the mesh currents that we need, and we've already identified those up here. So we have IA is equal to I1 and IC is equal to I1 minus I2. We need to substitute these in because these are basically what's going to relate this side to this side because we have them up here. So we can just rewrite that as -3 plus 2 times I1 plus 1 times I1 minus I2, and that's all equal to 0. Okay, so we can just simplify that a little bit. And at this point, we have -3 plus 3I1, and we have a value for I2, which was up here. I2 was equal to -1.5. So we can just give ourselves a little bit more space here, and basically just add 3 to each side. So we have 3I1 is equal to positive 1.5, and we find that I1 is just going to be equal to 1.5 over 3, or basically I1 is equal to 0.5 amps. And if we put everything into focus, just here we go, then we can see that I1 is equal to 0.5 amps. So this is equal to 0.5 amps. IB was equal to 1.5 amps. And for IC, it's equal to I1 minus I2. And so we have I1 is 0.5 amps minus I2. Well, I2 is actually -1.5. So we basically find that IC is equal to 2 amps. So if you wanted to label these on, IA would be 0.5 amps, IB 1.5 amps, and IC is equal to 2 amps. And that actually checks out with Kirchhoffs' current law at the junction as well. You have 1.5 plus 0.5 flowing in and 2 flowing out. So depending on what the question would be asking you, like if you're asking to find the power dissipation in the resistors, or often it's just asking you to find the mesh current themselves, which is the blue lines, or the branch currents, which are the green ones, depending on this kind of structure of the whatever you're being asked for. Basically just apply Ohm's law and then go on with that. So yeah, that's a quick introduction to mesh analysis. I would just recommend when you're doing KVL, Kirchhoffs voltage law around the loops, be really cautious when you're inputting in these positive and negative terms. And especially I like to put in actually the branch currents like that we've assumed, and then substitute them for the mesh current, because it's really easy to kind of accidentally get it backwards. But generally doing it this way, you won't make that mistake, and you'll actually end up with the correct answers. So anyways, guys, I'll see you in the next video, and we'll go over another example of mesh current analysis.